Right, so is the slide visible? Servo motor, can you see?
Yes, ma'am.
Right. So today, in the last class, we had done one control system component, which is often used for uh, sensing the error in a system, that is an error detector. So potentiometers, which are used as error sensors, were discussed. Now today we shall be going over to another component which is often used in certain systems, which is known as a servo motor. Now, as far as servo motors are concerned, servo motors may be either AC or DC type, but today we are first going to study the DC servo motor type. AC may be, if time permits, later on we will cover, but nevertheless, both the versions, that is AC as well as DC servo motors, are existent and possible. Now, since I'm presenting in the full screen mode, it's very difficult to admit other people. So anyway, let's continue. Now, just admit maybe one person. Sorry for the interruption, but not too many will be admitted after this. Right. So coming back, sorry. Most of the smaller motors used in servo mechanism application are AC and are of two-phase induction motor type. However, DC servo motors are also present, right? Now, what we are stating over there is that smaller motors which are used in servo mechanism application. Now, you would recollect that when I was, doing the introduction module, over there I had said something about servo mechanisms. Now, what are servo mechanisms? I had stated that in systems, in control systems, where basically the position, velocity, or acceleration is the quantity of interest, right? Is the signal in which we are interested in, that is the output signal of the system. In such cases, the system is known as servo mechanism. And also, I had stated that earlier people used to sort of classify servo mechanisms by themselves as control systems, meaning that those were the only control systems existent at a time. But of course, now it has diversified. The stream of control systems is not limited only to servo mechanisms. However, now, as far as servo mechanism applications are concerned, meaning that if we want to say position some load, right, or change the velocity of a load, then we would be using servo mechanisms. Now, as far as the motors in such applications are concerned, these motors actually are, you can say general or normal motors, in the sense that if I'm speaking of a DC servo motor, it is a DC motor, right? Similarly, AC servo motors are basically two-phase induction motor type. You can see that. So now, what uh, are the properties which, if existent in the motor, we can call it a servo motor, right? So, say for example, we do have a DC motor. Is that, essentially suitable for servo mechanism application? That is the question I'm saying, right? So, basically, servo motors are those motors which are used for applications where the inertia of the motor itself should be very small, right? Why the inertia should be small also has a reason, in the sense that since we are using such servo motors in servo mechanism application, if now say we have a change in the input voltage, right? Correspondingly, we would be expecting a reflection in the output position, meaning that if I increase the voltage at the input side, I would expect that there would be a change in the increase in the uh, increase in the position on the output side, right? So basically, the mapping of the input to output would be more or less linear for linear or proportional rather for a servo motor, right? So now for this, for any motor to qualify or for this property to hold for a motor, basically if you have a motor which has large inertia, naturally if you are applying voltage, it's not going to, the position is not going to change. So until you apply above a particular threshold, below that threshold, basically due to the inertia, the motor will not start rotating. So basically, such a thing is not what we would be wanting for servo mechanism application, meaning that a small change in the your input side should be reflected on the output side. When I say input side, I mean the voltage which is being applied. When I say output side, I mean change in the position or the velocity or acceleration, right? Whatever be the quantity of interest. So basically, that is one thing. Another thing is that if there is a reversal in the input side voltage, I would be expecting that, we would be expecting that the direction of rotation of the motor would be reversing immediately. So for such, I mean, requirements to be met, basically the motor should have low inertia. At the same time, I mean, though it should have low inertia, it should be able to generate a high torque. Why a high torque? Because say for example, we are using such a servo motor for changing the positional orientation of a say radar antenna. Okay, so the dish has to be pointed towards a particular target, maybe an aircraft in the sky or some fixed target which is mostly stationary but may move, and accordingly the directional orientation of the antenna has to change. So now, I mean, if the directional orientation of the dish has to change, naturally the torque generated by the motor should be high enough such that such a change can be made in the, I mean, your the orientation of the shaft has to be changed. So I mean, servo motors should essentially be able to produce a large torque, though they should have low inertia, right? Now, most of the smaller motors used in servo mechanism application are AC and are of the two-phase induction motor type, and their mechanical power varies from, you can see the range is written over there, 0.5 watts to 100 watts. However, DC servo motors vary in size. The range of variation is large, meaning the possibilities are large. They may vary in size from 0.05 horsepower to much higher ratings. Okay, so basically when they are used for large power servo mechanisms, DC motors, DC servo motors are used. Now, as I stated, servo motors are high torque, low inertia devices. So now if the requirement is to have high torque but a low inertia, okay, so let us go through it one by one criterion at a time. If the motor must have a low inertia, then what would generally be, I mean, would we go for a motor which has a larger radius or a smaller radius, meaning radius or diameter, whatever you call it, uh, basically, should the diameter of the motor be large or small for the inertia to be low? Can you tell me that? Can anybody try that? I just tried to admit a few people. Okay. For a motor to have low inertia, typically, regarding the size of the motor, should it have a larger diameter or a smaller diameter? Or for that matter, radius, whatever. What is, I mean, what's the relation between inertia and the radius?
Proportional to radius square.
Yes. So basically, I mean, if we want a lower inertia, we should typically make the radius big or small.
Small radius.
Yes, yes.
Small.
That's obvious, isn't it? So basically, the radius we would want to keep small so that, I mean, the motor has a lower inertia. But at the same time, the torque developed should be high. So for the torque developed to be high, what would torque be dependent on as far as the your size of the motor is concerned?
inversely proportional to R, the means size will be
No,
reduced.
radius is okay, but torque. Um, yes. If we have to keep the radius small, I'll reformulate my question rather. So if we have to keep the radius small, but at the same time we want to get a larger torque, what would we try to do?
Ma'am,
Yes,
torque is equal to moment of inertia times angular velocity, and moment of inertia equals to m times r square. So if r
yes,
is constant, then either m or omega can be increased to
right.
increase torque.
So yes, good. That's fine. So, okay, omega is okay, angular velocity. So that is, I mean, not related to the dimension as such. So naturally, now we would be wanting to keep the m, that is your mass, at a particular value. Now, if we want to, say, for example, keep the mass same while reducing the radius, what would we typically try to do? Say for example, I want the mass to remain at some capital M, but I mean, as per requirement, because I want to lower inertia, I have to reduce the radius. So what will I do with the, I mean, dimension? How can I keep the mass constant? What would I try to do then? You see, what I'm saying is, say I want a particular mass for my motor so that a particular torque is produced, right? So that mass is capital M. Now, at the same time, I have to reduce the radius. So if I reduce the radius automatically, I mean, without changing any other dimension, the mass will, be becoming smaller, right? So if I don't want to, don't want that to happen, which other dimension can I change so that I can keep the mass the same while reducing the radius?
Angular velocity then.
No, no, that is not related to the size. No?
We
Angular
can change the
velocity.
length.
Yes, exactly, right? So, I mean, basically what is done is typically with the construction, because the radius is, supposed to be small, the length of the motor is increased. So you can see actually the figure or the picture that you see over here, taken from the net, but the source is given over there as well. You can see that typically this is how servo motors are going to look. You see that the length is long. It's a long, motor, whereas the radius is small. Typically, if you, go to the machine lab or look at other motors, you will not be seeing, constructions typically which of motors which are going to look like this, isn't it? We have motors, typically the radius is large and you have the length comparatively smaller or comparable. But here for servo motor, typically the construction should be such that your motor length will be long, it will be large, whereas keeping the radius small. So this is how a servo motor is going to look like, right? That arises from the fact that high torque and low inertia are required for the motor to be operating as a servo motor for the specific application, that is a servo mechanism application. So it is a specialized form of a standard DC motor. It is a standard DC motor, but it is designed for specialized application and hence its form is a bit special. So it is designed to produce nearly linear changes in speed with proportional changes in the armature current. So, your uh, input side will be an electrical quantity. So, if say for example the armature current is the your is the signal that is the input signal. Now, the output being the speed. So, the change of the speed with respect to the variation in the input, that is the armature current, should be nearly linear, right? I mean, what happens if it is not nearly linear? There will be a change in the input, say the armature current, but the your change in the speed will be, say, large somewhere, small somewhere, because if I do not have a straight line characteristic, that is a linear characteristic, what will happen is the change in the input side will not be properly or proportionately reflected on the output side. But for servo mechanism application, that is a requirement. I would be wanting the load to be changing, the load, either velocity or position, whatever is of interest to us, changing proportionately to the input, that is the current being applied, or the voltage rather. So this feature permits it to change its direction as well and its speed of rotation smoothly with minimum mechanical stress on the control mechanism. So if the direction of the input current is reversed, we would be expecting that the servo motor will immediately start rotating in the opposite direction. So that would only be possible if it has low inertia, and only be possible for servo motors, that is. Otherwise, there will be a huge mechanical stress. If I just take a simple, I mean, DC motor, which is not specialized, and that is not in the special form of a servo motor, it will not be able to achieve these criteria. So that was actually the calculation, and so the same as what you have already stated. I'll just show you in a J is equal to MR square, and from there, basically, it's possible to explain. Now, coming to DC servo motors. So there are basically, I mean, different types of motors which are used for servo mechanism applications. That is, they are used as servo motors, series motors, separately excited motors, shunt motors, permanent magnet motors, or of course, I mean, motors which are not having a permanent magnet. I mean, all types or many of those types can be used as servo motors, DC servo motors we are speaking of at the moment. Now, most of the DC motors in control applications, however, have separately excited fields. However, I mean, other forms are also possible. Now, the control signal can be applied either to the field winding or the armature terminal. So, based on whether the input is applied to the field or the armature, DC servo motors are classified into field controlled DC servo motors or armature controlled DC servo motors. So, when the field is energized by the control signal, the motor is said to be field controlled. When the armature is energized by the control signal, the motor is said to be armature controlled. So those are the two broad categories of servo motors. Now, what we will be doing subsequently over here in today's class is that we will try to derive the model, that is the mathematical model of both these, that is the field control DC servo motor and the armature control DC servo motor. Also, we are going to try to compare between those two. So that is what we are going to do after this. So the first thing that we are going to do, or of those two, first we are going to look at the field control DC servo motor. So now you can see the field controlled DC servo motor configuration or circuit diagram over here. Yes. So now in field controlled DC servo motor, what happens is that basically the armature current is kept constant, and in an armature controlled DC servo motor, the field current is kept constant. So over here, since we are studying a field controlled DC servo motor, we will see that the armature current would be kept constant while the input is applied at the field side. So that is why it is called field controlled. I'll state that again in other words, meaning that we are applying the supply across the field terminals. So supply means what? The control signal. Now, the control signal means that basically, if you have a look at this small diagram on the bottom right, you will see this is the same diagram that we had once, seen earlier, schematic diagram of a position control system, where over there, at the time that I showed you this, we had looked at the error detector and its application. But here now you can see it's very small, but nevertheless some things are visible. You can see the motor is over here. I hope you can see the cursor. This is the motor, and what is being applied to the motor? Over here, this is of course, the control signal is being applied across the armature for this particular diagram, but that ignore that. The voltage which is being applied to the motor is being applied from the amplifier unit. So often in servo mechanism applications, you would be seeing that there will be an error detector, then an amplifier, and then the motor coming in, and then the motor shaft is going to be coupled to the load, and there may or may not be a feedback depending on the application. So basically, the input of the servo motor will be coming from an amplifier, which is often called a servo amplifier. So that is what is shown in the top diagram, the bigger one, where you see this side is going to the servo amplifier. So the servo amplifier is not part of this particular diagram. Rather, we are trying to say that from the other side, you see that left pointing arrow, it means that the servo amplifier will be coming immediately to the immediately before this servo motor unit, right? So the field voltage is the control signal which is being applied, because we are studying a field control DC servo motor. So VF is the notation. VF is the notation for the field voltage which is coming from the amplifier side, right? So this thing over here simply indicates that you would be having this VF coming from the servo amplifier, right? Now, since the VF is being applied across the field terminals, now let us describe the field circuit. So, in the field circuit, you see these are the field winding and the resistance shown separately. So, the inductance of the field side is denoted as LF. The resistance of the field side is denoted as capital R suffix F, and IF being the current to the field side, right? Field circuit. So, VF, IF are respectively the voltage and the current in the field circuit, and RF, LF being the resistance and inductance respectively. Now coming to the armature side. So as I stated, since we are studying the field control DC servo motor, basically the armature current has to be kept constant. So you can see this right. You can see this, that is the arrow being shown over here. This is the armature current, IA, and because it is field controlled, as I stated, the armature current is a constant armature current, right? So it is kept constant. Apart from that, you can see that the armature is shown over here along with the brushes, and you can also see that the armature resistance and the armature inductance are shown separately and denoted as RA and LA respectively, right? Also over here in the motor, a back EMF would be generated, and that is denoted as VB over here, right? That is as far as the electrical side is concerned, and the notations thereof are concerned. Now, as far as the motor is concerned, the motor shaft is shown by this dot dash line, this one, and that is going to be coupled to the load. You can just have a look at the bottom diagram over there, which is sort of, giving you an idea. And the, motor shaft will be, coupled to the load either through or without gear train, right? So gear train may be present, may not be present, but nevertheless, the motor shaft is going to be coupled to the load. So this is the motor shaft, and that is why load has been written over here. Now, this shaft will have its own angular position denoted as theta m, that is the angular position of the motor meaning motor shaft, of course. Tm is the torque produced by the motor, right? And Jm and Fm are the moment of inertia and viscous friction coefficient respectively. Proper units you can see are written over here. So Tm is the torque developed in Newton meter, Jm is the moment of inertia in kg meter square, Fm is the viscous friction coefficient in Newton meter per radian per second, right? So basically, those are the units. So now, in order to derive the model for this, by model I mean a mathematical model, and also I mean that we are going to find out the transfer function of the field controlled DC servo motor. So for that now we will be proceeding. But before that, what we will be, looking at is that there are certain assumptions which we should keep in mind, because otherwise we would not be able to derive the relations. What are the assumptions over here? The first one I've already stated. Because it is a field control DC servo motor, a constant armature current IA is fed to the armature. So IA is constant, right? Also, another assumption is that the air gap flux phi is directly proportional to IF. So we would be neglecting the effect of any distortion or whatever. So basically, phi is assumed to be proportional to IF. So as a result of that, phi is equal to kf IF, where kf is a constant having proper units, of course. What would be the units over here? You can see this is the flux per current would be the unit, whatever be the unit of your flux and current, kf would be having appropriate units. So phi is equal to kf IF, right? Next, we come to the torque developed by the motor, that is Tm. Now, Tm is directly proportional to the flux as well as the armature current. So, Tm is proportional to phi and Ia, and we can write Tm is equal to some constant into phi into Ia, right? So, we denote that constant by Kn prime over here. So, this is what we get, right, as the developed torque in the motor. Now, from here, we are going to replace phi by, if we see phi, we have said is equal to kf if, because we've assumed that phi is proportional to if. We are going to replace that over here. So, you see, Tm becomes equal to Km prime kf if Ia, right? And now, we can further, try to rewrite that as we are going to make an assignment, that is, let us assume that, okay, before that let me tell you something. Now in this expression over here, if is of course a varying quantity, right, whereas Ia is constant, isn't it, because it is a field control DC servo motor. Armature current is constant, so we can take this Ia also and combine it with some other constant. So what is, that is what has been done over here. So Km prime into Ia together is a constant and is denoted by another constant, which is Km, right? So by, assigning this, that is, if we assume that Km is equal to Km prime Ia, because of course Ia is a constant, we will get Tm is equal to Km Kf If, right? Now, taking the Laplace transform, we will be arriving at this, that is TMS is equal to KMKF into IFS. That is the relation between the field current and the torque in the motor. However, now, can you tell me one thing? That is, as far as the field control DC servo motor is concerned, as I told you, we will be going through the steps for finding the transfer function of this servo motor, right? Now, transfer function means what? We want relation between the output and the input. Now, what is the output of this field control DC servo motor? What signal is the output? Can anybody tell me from whatever I've told you so far? Which quantity is output for this motor? Which signal is the output for the motor? What are we trying to achieve? Achieve means I've told you where it is used, and what we would be trying to do by using this servo motor. So that should give you a hint regarding what should be the should be considered the output of this DC servo motor.
Torque.
Uh, no, not torque. Indirectly, torque, of course, is related, but what exactly would we try to do? Servo mechanism does what I mean.
Speed.
Yes, right. So speed or position, I mean position or its derivatives rather. Okay, speed you can say. So basically, uh, over here in this particular, I mean, DC servo motor, the output of interest would be theta m or its derivatives. So I mean, if you write the transfer function in terms of, I mean, taking theta m as the output, that's going to serve the purpose. And if it is theta m dot, naturally another s will be included somewhere or taken out. So basically, I mean, either position or velocity would be the output. In this case, we are considering the load position or the motor shaft position rather as the output, right? Now, what is the rather, what is the input to the system from what I have described so far?
A field current, IF.
Okay, good again. So field current, but we are not applying the current. What we are applying is we are applying the field voltage because we are applying the voltage which is the control signal and accordingly a current will be flowing in the field circuit. But good guess, right? So here basically the input quantity is Vf, right? So if we want to derive the transfer function of the field control DC servo motor, we would try to obtain an expression which relates theta m to Vf, meaning the output to the input which is being applied, right? So we would have to actually, I mean, over here, get a couple of more relations which are going to enable us to find the relation between theta m and Vf, right? So as a starting point now, what we are going to do is we are going to write down the your equation for this field circuit itself. So you know that Rf is the resistance and Lf is the your inductance. So from there, first of all, we would be going for the equation of the field circuit. Now, can you tell me what the equation of the field circuit is? You would, I mean, we collect that we also the
EF
diagrams.
equal to RF IF plus LF DIF by dt.
Yes, DIFDT. So yes, that is correct. The simple thing, right? So VF is equal to IFRF plus LFDIFDT. That is the equation of the field circuit, right? So now, of course, we are going to take the Laplace transformed equivalent of that, which is basically VF, VFS is equal to RF plus SLF whole into IFS, right? So that actually has, I mean, given us a relation between VF and IF, right? And on the previous slide, we had a relation between TM and IF, right? So now, of course, we would try to relate Tm with what? With the shaft position, that is theta m, because I said we want ultimately to find a relation between theta m and Vf, right? So we proceeded in one direction. One direction means that on the input side, the field circuit relation we have got. Also, we've got a relation between the torque and the your field current. That much is done. So the only thing left now is to relate the torque to the output shaft position, right? So can you tell me what would be the relation? You would recollect that we had denoted these the torque by the developed in the motor as Tn and the angular position as theta n. Also, Jm and Fm were denoted as, I mean, were denoting the moment of inertia and viscous friction coefficient respectively. So now, I mean, that hint has been given. What would be the relation between the motor torque and the shaft position?
It is proportional to theta dot speed.
Mm, but there is a distinct relation between torque developed and your angular position or
K phi
velocity.
omega. It is
No,
K
no, no. You
I
have
theta
the
double
moment.
dot.
No, you have the moment of inertia and viscous friction coefficient as well. That is the hint. You have to consider those as well. JM and FM also will be, you have to consider those, the effectors. How is the torque related to your moment of inertia? And for that matter, the viscous friction coefficient. I'm sure you know this. Even from the units, you would be able to say the torque unit is what? Meters, isn't it? And now consider JM and FM. Forgot. That is a purely mechanical relation, I agree, but isn't it this, I mean, isn't this the relation between your torque and your angular velocity and angular velocity and angular acceleration? Tm equal to jm theta m double dot plus fm theta m dot. Do you recollect this relation? You had done it somewhere in your signals and systems, I think, and even before that, maybe in some mechanics class. Do you recognize this expression? No?
Yes, ma'am.
Yes. So basically, the relation between the torque and the angular position of the shaft would be given by Tm is equal to the moment of inertia Jm into theta m double dot plus viscous friction coefficient Fm into theta m dot. So now if we take the Laplace transform, this is what you would get. So Tm is equal to Tms is equal to Jms square plus Fms into theta m s. So over here now you can see that I can take out S common, which actually means that torque will be proportional to I mean theta m dot, because if I take out S over here, that would amount to d theta dt if I look at the time domain expression. But nevertheless, this is what you get. So now, I mean, all the basic relations or expressions have been written, basic in the sense that we have now a relation between VF and IF. We have another relation between TM and IF that's written on the previous slide, right? And then we have a relation between TM and theta M as well. So now we can try to just, I mean, sort of substitute and rearrange and get a relation between theta M and VF, because ultimately that would be giving us the transfer function. So just this, so JM and FM. So, I mean, going through the steps one by one, you can see Tm is equal to Jms square plus Fms into theta ms, that is written over here. And this substitution, this expression directly comes from, you would recollect on the previous slide, we had the expression TMS is equal to KMK of IF. So instead of TMS, we have made this substitution, right? And that is equal to KMK of IFS, right? So now over here, again, in place of IF, we are taking from this, that is equation of the field circuit, where IF is equal to VF by RF plus SLF. So IF has been replaced by this, right? So that now, over here we find that this is a relation between theta m and VF. So just rearranging and writing such that we get in the form of theta ms by VFS, that is the output displacement by the input voltage to the field. This is what we get. Just rearranging and putting it. So that is equal to Km Kf by S whole into JMS plus Fm, again whole into RF plus SLF. So that is the transfer function of a field controlled DC servo motor. Okay, this one So now, in the next step, further simplification has been done such that this is expressed in the time constant form, right? So in order to do that, what has been done is Fm and Rf have been taken out common, and it is expressed as 1 plus S tau m, where tau m is given by Jm by Fm, which is also known as the time constant of the motor. So tau m is the time constant of the motor, and that tau f that you see over there is Lf by Rf, which is also known as the time constant of the field. So this particular expression gives us the transfer function in the time constant form, right? So from here now we can try to draw the block diagram of the motor. Over here, of course, the block diagram is very simplified in the sense that we will have this as the block diagram of field control DC servo motor, where you find that the input is VF, the output is theta m, and this is what comes inside the block. It is the whole transfer function that we had derived in the time constant form that has been put within this block. So this is the block diagram of the field control DC servo motor, and this being the transfer function, right? The whole thing. So now next we come to the other, configuration, that is the armature control DC servo motor. So over here again, the diagram for the armature control DC servo motor has been drawn, circuit diagram. So here again, since the input is going to come after, rather from the servo amplifier unit, this arrow with the servo amplifier is written over here is shown, means that this side is going to be plugged on to the the servo amplifier, or rather the signal that is input to the system is going to come from the servo amplifier side. Now, as this is an armature controlled DC servo motor, here first of all the field current is going to be kept constant. So you see the field is drawn over here, but the field current, that is IF, is going to be a constant, right? At the same time, since it is an armature controlled DC servo motor, the voltage, that is the input signal, is going to be applied at the armature side, across the armature. So that is also denoted as VA, that is the armature voltage, or voltage across the armature, right? Apart from that, again, the parameters of the armature are denoted as RA for the armature resistance and LA for the armature inductance, and VP is denoting the back EMF across the armature. The armature, you can see, is drawn over here. The shaft again shown by the dot dashed line, and theta m is the angular position of the shaft, Tm being the torque developed, Gm and Fm being respectively the moment of inertia and the viscous friction coefficient, right? So now again, by a similar sort of approach as we did in the case of a field control DC servo motor, first of all, we identify the assumptions that have been made. So the assumptions are that, number one, the field current is constant, because this is in the armature controlled mode. The field current is constant. So IF is a constant field current which is fed to the field, right? Also, we are assuming again over here for this configuration as well, that the air gap flux phi is directly proportional to IF. So that makes phi is equal to kfif, where kf is the constant, right? Also, the torque developed is going to be, I mean, it's denoted as Tm, and it's going to be proportional, directly proportional to phi and Ia, which enables us to write this, that is Tm is equal to some constant Km prime into phi into Ia. So this expression till so far is similar to that in the case of a field control DC servo motor. Now phi is equal to, you see, kf if. So that substitution has been made over here, and we get this, that is Tm is equal to Km prime to kf if into Ia, right? Now over here, since this is an armature controlled DC servo motor, the field current is constant, so that this first three terms over here, that is Km prime, Kf, If, all these are constant. So all three of these are denoted together as some constant, some other constant, K suffix I, so that we can write this as being equal to Ki into Ia, where Ki is given by Km prime, Kf, If, and we know that If is also a constant, Kf and the Km dash obviously are obviously constants as well. So now we have come to the expression, I mean, we have been able to simplify the expression as Tm is equal to Ki into Ia. From there, now taking the Laplace transform, we can write Tms is equal to Ki into Ias, right? Also now, since this is the armature controlled DC servo motor, it implies that basically we would have to write the circuit equation for the armature side, and I mean, because the armature is being excited over here, we also would have to consider the back EMF when we are writing the equation. So for that, now, I mean, as a starting point, the expression for the back EMF is also written over here. So back EMF, we know, is going to be proportional to the speed, right? So basically Vb is equal to some constant into theta m dot, that is d theta m dt. So Vb is equal to Kb into d theta m dt. So that is the expression for back EMF. So from there now, we are going to write the equation for the armature side, and also some other relations which are going to, I mean, enable us to find the transfer function of this armature control DC servo motor. So here again, first of all, before going to the next slide, I'll sort of deliberate on what should be considered as the output of the system and what should be considered as the input of the system. So again, as it is a DC servo motor, the angular position is going to be considered as the output quantity, that is theta m or its derivatives, of course. So theta m is the output of interest for this armature control DC servo motor. On the other hand, what is the input which is being applied over here? The input signal in this case is V suffix A, right? That is the armature voltage. So that now, I mean, we would be writing, relevant expressions, and we would be trying to rearrange and substitute and all that, and we would be bringing an expression relating VA with theta m. So I mean, we are sort of trying to, before going into the derivation itself, we would have to keep these in mind, meaning which is the output, which is the input. Otherwise, we'll get lost midway and we will not be able to find out, I mean, what exactly we want. We will get confused. So that is why, I mean, even before starting, we've identified what the input is going to be, what the output is going to be. So now we can write the relations and then try to get rid of the intermediate variables to link or obtain a relation between theta m and VA. So now, okay, this slide, the whole thing is visible. Nevertheless, we'll go one by one. So the first equation that we are going to write is the equation for the armature circuit. So here, VA is equal to IARA plus LA DIA dt plus the back EMF VB. That has to be considered over here, right? So from there now, taking the Laplace transform, we have VAS is equal to RA plus SLA whole into IA S plus VBS, right? From there now, VBS we've already written on the previous slide. So instead of VBS, we substitute KB into theta m dot was the, time domain expression. So that is S theta m S, right? So KB S theta m S actually has been substituted in place of VB. The rest of the things remaining the same, right? So now this, relation, and this is a relation between, you can see VA and IA and theta m, all the three are there. So IA, in the next step, what has been done is IA is equal to, it has been written in this form, that is equal to VA minus KBS theta ms whole divided by RA plus SLA. This is just, reorganizing and writing, right? So now also we know, or rather on the previous slide, we stated that TMS is equal to some constant Ki into IAS. So that, uh, I mean, this over here in this expression now, if we substitute IAS from here, this is what we get. So Tm is equal to Ki into Ia, which is basically this. That is the rest of it. You can see it's evident. If you cannot understand, I hope you can see the cursor moving. So in case you are confused, you can ask me anyway. So this is Ia that has been substituted over here. So now again, yes, we have a relation between Tm and Va and theta m, but we are ultimately trying to get an expression relating Va and theta m only. So Tm again, we are we are trying to obtain an expression relating Tm and theta m. It's the same expression that we derived in the case of a field control DC servo motor, that is Tm is equal to Jm theta m double dot plus Ff theta m dot. So taking the Laplace transform, this is what we have. TMS is equal to JMS plus FM whole into S theta m S, right? So from this expression now, Tm has been replaced by JMS plus FM S theta m S, right? And that is equal to the rest of the things, that is these have been written as they are over there, right? So now we can see that in this, particular expression, we have the variables theta m and Va only. So we are, nearing our goal of getting the transfer function. Now just, sort of manipulating and reorganizing and collecting terms and writing it is what is required. So from this point onwards, you collect terms containing theta m and okay, first this has been multiplied to that side, so that's what you get, and then collecting terms with theta m on the left side and with Va on the right side, and then dividing by Va, this is what we get. So we ultimately arrive at the transfer function, which is theta ms by Vas and given by Ki by S into Jms plus Fm whole into Ra plus Sla plus Kb Ki S, right? So this is the ultimate form of the transfer function that we have arrived at for the armature control DC servo motor. So again, we can actually try to write this in the time constant form as this. That is, we take out Fm and Ra common from this, and this is what we get. So it's written in the time constant form, where this 1 plus S tau m, this tau m is equal to Jm by Fm, which is also known as the mechanical time constant of the motor, and tau a is given by La by Ra, which is also known as the armature time constant, right? Now, in this transfer function, we find that this is a bit different from in structure, apart from, of course, um, your variables and notations and all that. Apart from that, we find that structurally this transfer function is a bit different from the previous one, that is the field controlled DC servo motor transfer function. In that, here we have an additional, term in the denominator as plus KBKI. This sort of thing was not present in the field control DC servo motor. However, let us try to see what the implications of this may be. But before that, what we are going to do is we are going to try to draw the block diagram. So in order to draw the block diagram, what we do is we divide the numerator and denominator by this quantity, that is this one, or in fact, if we proceed from the next one, that is the time constant one, this first term in the denominator is what we divide by. So numerator and denominator are divided by this, that is RAFM S whole into 1 plus S tau M into 1 plus S tau A. This. So doing that, the same expression, that is theta ms by VAS can be, this is the form that we get, is written as you can see over there. I'm not reading it out, it's a huge expression. So in this expression now we can identify certain things, that is we can put this Ki by RAFM S 1 plus S tau M whole into 1 plus S tau A. This, if we say, is the forward path transfer function, then we can we can see that this can be identified in the form of a feedback control system, where and this portion, the numerator portion, is denoted as ds, that's the forward path transfer function, and the denominator is 1 plus that portion multiplied by skb. So this s into kb can be denoted as the feedback path transfer function, right? So if we take hs is equal to skb and ds is equal to, as you can see over here, the numerator, that this whole expression for the transfer function boils down to gs by 1 plus gs hs, right? So from there now we can try to draw the block diagram as a feedback system like this, as shown over here in this diagram. In this diagram, note certain things. First of all, that the forward path transfer function in this diagram has been broken up into two parts. One is the electrical quantities and the other as the mechanical part of the transfer function. So basically, this denotes the mechanical portion of the transfer function, the forward path transfer function, and this denotes the electrical part of the transfer function, right? When you are taking both together, naturally these are cascaded, so it's going to be multiplied. So if you say, okay, this is G1, this is G2, so G is equal to G1, G2. So basically when you multiply these two, you're going to get G, that is the forward path transfer function, right? So everything over there. Also, additionally, now we find that, okay, VA is the input to the system that is there, theta M is the output that is there. And in the feedback part, we have the transfer function Hs, which is given by S into Kp, and it comes with a negative sign, because if this were not a negative sign, actually this plus sign would have to, it would have changed, it would have been minus. If this is a positive feedback, that would have become minus, but nevertheless, if you just derive the transfer function over here, we're going to get back this. That's what I mean, right? If the sign over here is negative, which is what we have. So this is the overall block diagram of the armature control DC servo motor. Now tell me one thing, that is, we have the feedback path over here, and the feedback path element is given by skb. So now, what signal is being fed back over here? So you see, this is the angular position theta m. From there, the signal, the feedback signal, is coming via skb and then being fed back to this point. So basically, what is the nature of the signal which is being fed back? Can anybody tell me? Nature means physically what sort of quantity is it? Is it the position or something else? The signal over here I'm speaking of, after the skb block.
And velocity.
Yes, very good. So it is the angular velocity that we are inherently feeding back. But of course, keep in mind that this overall block diagram is the configuration of an armature control DC servo motor. Nobody is going to take a connection from there and connect it. Inherently, that feedback is there within the motor itself. Okay. So now, okay. The effect of, actually, if you recollect, this skb actually came from the back EMF term, right? So here, the effect of back EMF is represented by the feedback signal proportional to the speed of the motor, as you have correctly stated, right? So it's proportional to not the position, but the speed of the motor. It resembles the tachometer feedback control system, where you have a speed feedback. It's sort of like that. But here, of course, it is implicitly within the system itself, the speed feedback. Now coming to a comparison, which is going to be the last slide that I show you today, but some discussions are required. That is, basically now we are going to compare between the armature control and the field control configurations for the DC servo motor. So we have by now actually derived the model, mathematical model, that is a transfer function of the armature control DC servo motor and the field control DC servo motor. And both are apparently, I mean, third order transfer functions, if you would have noted. However, I mean, this, okay, let me just show you the previous. No. Okay, so however, this transfer function that we, this is the basic form of the transfer function from where we actually, I mean, got the block diagram. So here now, the armature inductance is something which comes over here, and usually the armature inductance is negligible, very nearly equal to 0. So if that is nearly equal to 0, it would imply that your tau A would approximate, I mean, almost be, also be very nearly equal to 0, and that would imply that this transfer function that we have derived would boil down to a second order transfer function rather than, because I mean, you have the SLA, so S is multiplied with LA, so if LA is 0, that means that this becomes a second order denominator only. So that, I mean, the armature control DC servo motor transfer function boils down to a second order transfer function when because rather the armature inductance can be neglected, it is negligible. On the other hand, the field inductance is not negligible, so that the field control DC servo motor transfer function remains a third order transfer function. So that is the first point that we have over here. Let us read through it. Inductance in armature circuit can usually be neglected. The denominator of transfer function in an armature control operation reduces to a second order equation, whereas for the field control DC servo motor, field inductance is not negligible, and it remains, the transfer function remains a third order transfer function, right? The next thing, I mean, of next point of difference that I would like to point out is that in the armature control DC servo motor, there is an additional term which has come due to the back EMF. If we just look at that term, I prefer this this basic form, because over here you can see everything, because within tau A and tau M certain things are hidden, so that's why I'm showing this form, easier to visualize from here. Now here we find this in the denominator, that is, we have an additional term plus KBKIS, right? This has come from the back EMF. Now this is a, you can see it's a first order term. Now basically, and we are also saying that, I mean, because LA is negligible, the overall transfer function is a second order transfer function, meaning the denominator is a second order. Yes, it is a second order expression. So now, I mean, what has happened is, if you look at the denominator, you will be having one term containing S squared, Jm into S squared will be what you have. And then you have Fm S into Ra. So basically that is a first order term. Another first order term, which is Kb Ki S. Now, I mean, this first order term would be actually contributing to some added damping in the system. If you recollect, in your second years, you had studied in your signals and systems, you had thoroughly studied second order systems, right? And over there, if you recollect, which term is responsible for the damping of the second order system? Is it the constant term or the first order term or the second order term? Because in the denominator you have, say, S square plus 2 zeta omega n s plus omega n square. That was a standard denominator in the second order transfer function. So which term is specifically responsible, which order term is specifically responsible for the damping?
Say first order term.
First order term, right? So I mean, the coefficient of the term containing S is responsible for the damping. So over here now we find that apart from the damping which is produced due to Fm and Ra, because we have S into Fm into Ra, that will, I mean, produce damping. Apart from that, we also have the back EMF term, that is KBKIS, is also a first order term. So there is, in this armature controlled mode, there is an added damping which we get due to the back EMF effect. On the other hand, in the field control DC servo motor, first of all, it remains a third order transfer function, and also the effect of back EMF does not explicitly come in, because we write the equations for the field side only, and I mean work with the field voltage and field current and all that. So basically, back EMF effect does not come in the overall model. It does not affect the overall model. So that means that, I mean, there is no added damping present due to the back EMF in the field control DC servo motor. So that second point over here, let us read through it. In armature controlled operation, an equivalent damping, that is electric friction actually, due to the back EMF effect, in addition to the damping due to RA and FM is present. The back EMF effect does not appear in the field controlled case, and the entire damping must come from the motor and the load. So basically, that is another point of difference between the armature controlled and field controlled operations. The third one and the last one is that in the armature controlled DC servo motor, the armature voltage is being applied, and that would actually, I mean, typically the armature circuit should be able to supply a greater amount of current. That is, IA is typically going to be, I mean, large, and basically the armature circuit should be able to supply that rather than, I mean, that in case of a field controlled DC servo motor where the field has to be excited, field current typically being much lesser. So in the armature controlled operation, an amplifier which is able to supply that large current would have to be used, because it has to supply the armature current which is typically large. On the other hand, in the field controlled, I mean, mode, basically such an amplifier may not be required. So the amplifier used to energize the armature circuit must be able to supply a greater amount of current in the armature controlled mode rather than in the case of the field controlled DC servo motor, where it were to energize only the field circuit, which does not require a large amount of current. So that actually brings us to the end of this module, that is the DC servo motor and the comparison. So in the next class, we are going to do an application, which is a remote position control system, where we would be using the DC servo motor your model, as well as we would be requiring the error sensor model, and all those would be used for a practical or physical system, the model of which again is going to be derived. So I just stop the recording first and the presentation, but I'll take your attendances.